My name is Andreas Zimbal, and I'm chair of Section 3, Neutron Metrology of the CCRI. And my role is here now to introduce the speaker of today, as it will be a neutron topic, a person well known to the community. It will be given by Vincent Gressier. And Vincent is very familiar with neutrons. He worked decades on neutron metrology. And just a short introduction. Vincent started, or during his PhD, he worked on neutron cross-section, on the experimental determination of neutron cross-sections on Neptunium 237. And later in 1999, he joined the RSN, the neutron metrology group, and he worked on neutron metrology, neutron spectrometry, and he was setting up the calibration facility with monoenergetic neutrons at RSN. And then since 2018, he was head of the neutron metrology lab at RSN. So he is very, very familiar with neutron metrology. Vincent is also a member of CCRI 3 neutron metrology since 2003 and was chair of Section 3 since 2015 until 2021, where he moved to the BIPM, where he is still now located as director of the ionizing radiation department and executive secretary of the CCRI. But this is not the role under which he is, so to say, speaking to us today. But due to his outstanding and very long experience in neutron metrology, he volunteers to give a talk about the basics which you need if you want to set up a neutron calibration facility. So the title of the talk is Getting Started with Neutron Calibration, and we are very curious, Vincent, to listen to your talk.
Okay, thank you very much, Andreas, for your kind words. And so let me share the screen. Starting with neutron calibrations first, I would like just to say that we are not in this webinar. I will not go through all the topics that cover neutron metrology, because if you want to discuss everything, then you will have to discuss what is a neutron device calibration, which could be full characterization, calibration factor, calibration methods. For that, we have to investigate what is a neutron device response. Could be a variation with energy, could be a variation with angle. And you will also have to discuss about what is neutron spectrometry, because we have to determine the neutron fluence energy distribution, also the neutron angular energy distribution. It will depend on the neutron fields, could be ranged from thermal neutron fields up to high energy or high intense pulse, even pulse neutron fields. You will have to deal with a lot of standards and with some quality issues in order to be able at the end to go to different kind of quantities, about international comparisons, CMCs, and all these things. So I will restrict the talk of today, which is starting with neutrons, to this, which is what is calibration coefficient and methods. We will deal only with radionuclide neutron sources. We will speak only about the ISO standards 8529. And of course, we'll discuss a little about quantities and transfer instruments, but not else. And there will be, I'm sure, Andreas, further other webinar on neutrons, which will cover the other topics. We already had one by about high energy neutrons beginning of last year. And this is something which will continue, hopefully. So calibration. So calibration, the definition of calibration is a set of operations that establish under specified conditions the relationship between values indicated by the neutron sensitive device and the corresponding non-values of the quantity to be measured. So we will see that after. It's just something very, very easy to write. But what is behind is that if you want to establish this correctly, you have to determine the response for the full range of radiation energies, even of type of energies, and angle of incidence for the use the instrument will be intended to. And you will face very quickly some problems because you have a large range of neutron energies and intensities. In neutron, we are facing energies varying from a few milli-electron volts to tera electron volts. So there is a large scale of energies that we have to cover. The neutron fluence rate is also going from very low level to very high level. So we are speaking about 17 order of magnitudes. The neutron incidence can be also parallel beam, but also could be multi-directional fluxes in both energies and intensity. And neutrons are never alone. You cannot have a pure neutron field that doesn't exist. You will always have other radiation like photons, beta ions with various proportions. So if you want to characterize every parameters in an experimental way, that's impractical, both in terms of time and cost. So that's why what is today used in neutron metrology is we use models and we validate these models and we validate these instruments, modeling instruments, through a few key neutron reference fields and make extrapolation, interpolation between those. Okay, so now the question is, how should someone start a neutron activity? So first, he should start by only focusing on calibration coefficient and factor. It is the most simple form of the calibration. It's just a factor by which you multiply the reading of your device in order to obtain the value of the quantity that you are trying to measure in a given reference field. So just three terms: calibration coefficient, ratio between the quantity, could be the fluence, can be the dose equivalence, could be the rates of these two quantities, and the reading of the device, which important part here is the corrected reading of the device. And we will see that most of the slides that will follow this webinar will be dedicated on how to correct the reading of the device. So limitation is that we can only use this calibration coefficient if this instrument is used exactly in the same radiation field that's where it has been calibrated, or if you have a pure flat response instrument. So at the end, such calibration coefficient and factor should be restricted to check the neutron response stability of a device and not validated fully. Just a note now to all our colleagues from dosimetry and radionuclide metrology, the typical uncertainty for a calibration of an instrument is about 5%. So the best reference we can have is about a few percent. So the calibration is this kind of order. So don't be surprised if we are speaking about correction about a few percent. It's neutron in the neutron field that's usual. So what is the main need is for radiation protection instruments. So most of the neutron fields have energies below 20 MeV. The neutron dose is coming mainly from the fast energy range. So in the fast energy range is the one here in yellow, so between 10 keV and 20 MeV. So this is how in neutron metrology the energy ranges are categorized. It's not the same way in nuclear physics, in nuclear reactor physics. There are other things. Neutron metrology is only these four parts. So the ranges is between 1 microsievert to 1 sievert integrated, and the rates is between 0.1 microsievert per hour to 100 millisievert per hour. So this is the kind of factors you should have in mind when you try to start a neutron activity. And the easiest way to match this first requirement is to use a radioactive neutron source. So why? Because you will have a high stability during the measurement. If you use an accelerator-based neutron source, it will not be so stable with variation due to current, with a lot of parameters. You have a tabulated energy distribution, which covers most of the fast energy range given by the standard ISO 8529. And there are two complementary sources that are available and many described. The americium barium 241, which can focus on the 3 to 8 MeV energy range, and the Californium 252, which will focus on the 1 MeV to 4 MeV energy range. So you have the energy distribution, americium barium here, Californium here. The emission rates of these sources can be calibrated with today less than 1% uncertainty with the manganese-based method. I will not go in details, maybe another webinar for that. So for the neutron sources to start with, so you have ones for this americium barium 241. It's a alpha emitter from the americium, which will generate in barium the neutrons. The mean energy is about 4.4 MeV. You can have on the market up to 10 to the 8 second minus 1 emission rate, which means about 1 millisievert per hour at 1 meter from the source. The half-life is 32 years. And for the californium, which is a spontaneous fission process, the mean energy is a little two times below. But you can have up to 10 to the 9, this one, in terms of emission rate, meaning 10 millisievert per hour at 1 meter. But the half-life is far lower. An advantage is that you can, and you have on the ISO standards also, a reference heavy water moderated californium field, which is this one. So you still have this fast part, which is a non-moderated, and then you have up to the thermal field, you have energy distribution, which gives you a wide energy range field, which we can consider as a kind of realistic neutron field. What are the disadvantages of these sources? For the americium barium, one of the problems is the regulation, because the activity for an americium barium is calculated on the emission of the americium, so meaning of the alpha, and not on the neutron emission. So if you consider, for example, an emission rate, a neutron emission rate of 10 to the 7, it's about 200 gigabecquerel source. And if you compare for the same emission rate of neutrons, for the californium will only be 0.1 gigabecquerel. The problem also for the americium barium is that there is no moderated reference field, so it's just americium and nothing else. You have a high photon emission rate, and the variation in the energy distribution is also more dependent of what is the source size, what is the type of the source, what is the manufacturer, and you should add an uncertainty about 4% in the fluence to dose equivalent energy coefficient. So I will not explain all these quantities, but the fluence is the number of neutrons per square centimeter, and it is what we measure in neutron metrology, and we just apply a coefficient to convert from fluence to any kind of other quantities. So, but due to the energy distribution uncertainty, you have to add 4% in addition to this conversion coefficient, compared to only 1% for californium. What are the disadvantages for the californium 252? First, the short half-time. After 10 years, you will have 15 times less neutrons than the one you have paid for at the beginning. So that's also a problem. You have a contaminant, which is when you buy a californium source, you always have a mix of 252, 250. For a new source, there is very low percent of a few percent maximum of 250 californium, but with time, because the half-time is far lower for 252 than 250 isotopes, of course, this ratio will not go in favor of 252. And the second point is, or the third point is a very high cost. If you want to have a 10 to the 9 emission rate source for californium, today is more than 500 kilo euros. So that's something which is also problematic in terms of budget. I don't say that americium barium is cheap, but it's not as high as for californium today. So for all this reason, the best practical choice, but that's my personal opinion, but can be shared by others, is to start with an americium barium. So you have your source. Now, first things to do, if you can, ask for a calibration of this source. So the calibration coefficient is just given by the, as a reminder, ratio of what the source provide and what you measure. And what the source provide is a factor between the emission rate B multiplied by a correction factor for anisotropy, divided simply by the surface of the sphere, emission rate in all in wall space, 4p d. So that's easy. if you get these two factors, then you just a small calculation, of course, in vacuum, without source decay, without any other correction factors. And this calibration is generally performed by NMI and DI. So these two parameters is first, you should ask for the emission rate, and it is given generally by the Manganese-Bass method with about 0.5 to 1% uncertainty. But you should also ask to the anisotropy correction factor. So F theta is what is the variation of the neutron emission in this direction. So the axis of the cylinder. The source is always in the form of a cylinder, compared to what is at 90 degrees, which is in the direction that we generally used, compared to 100. So this is the variation you can see here. And there are a few percents of variation due to the size, due to the protection, due to also the direction, etc. But once you have done this, the other question is my source homogeneous in all the directions in this plane of 90 degrees? And this is what is F90 alpha. So these two factors, generally people are only focused on this one, but this one is geometrical. This one is also important because sometimes you have not an homogeneous distribution of the radioisotope inside, and depending where you are, it can provide additional uncertainties. So for americium barium, as I previously said, there is also attenuation is a lead surrounding the source. And to cut the photons, you should put a lead to surround the source, and this has to be taken into account in your calculation. Or you cannot have a calibrated source. So in such a case, the best way is to use a transfer instrument that you will calibrate on the same type of source, if possible, of the same size and activity. That's easier, but will provide you larger uncertainties at the end and the calibration factors that you will provide to your customers. The transfer instrument that is most often the time used is a survey meter, like a Berthold, LB6411, SmartRAM. There are a lot of possibilities, but you could also use just one or several bonus spheres. You can use a long counter. I will come back to what is a long counter later, etc. And the first step is, okay, I put my instrument on another laboratory, and they provide me a calibration factor, which is the ratio between the H and the measurements. And I do exactly the same measurement in my lab. And I guess so, this kind of relationship. So in such a way, it's easy to just say that what is the reference in my laboratory is just the measurement multiplied by the calibration factor I've determined at the reference laboratory. So of course, you have to take into account additional uncertainties. If there are some differences in energy distribution, there are also some correlations, but that's not something which is too hard to solve. So my advice is also to place a detector, not your transfer instrument, at a fixed position to monitor the neutron field repeatability. You can just check, okay, I have my variation of activity due to the decay life, but sometimes there are some strange things, and it's always good to have at the right place, at the right and always the same place, a detector that monitors that everything is repeatable. And if you have some doubts, could become from your monitor, then please double check with your transfer instrument to see if there is a problem with the source or with your monitor. If you have to access to the number of counts, it's also a good idea to calibrate your instrument both in terms of neutron dose equivalent and neutron fluence. Then you will avoid to go to one to the other quantity by just adding uncertainties due to the uncertainty in the energy distribution. And the linearity of the transfer instruments should also be known. And we will discuss this later. And this can be done together with the calibration or at your own facility. So, okay, we have a source now. We need an irradiator and a facility. So the main idea is you should minimize as far as possible the scattered neutron contribution. And if you see what is written in the ISO 8529, the contribution to the instrument reading of the scattered neutron should not put an increase of more than 40%. It means that you should put your source in the center of a large room, at least 8 by 8 by 8 meter, or 12 by 12 by 6, or 8 by 8 for 8 meter, if no concrete roof. So that's what is written in the standard. The source should be at several meters above the ground, at least 2 meters. You should use low scatter light elements like aluminum, hydrogen-free. Minimize the materials around the source. One big contributor in terms of neutron scattering is the source holder by itself. And the storage place of the source, when not in use, should minimize the neutron background as a calibration point. So I provide you here an example of what is done at PTB. At PTB, you have wires. You cannot see the wires. And here you have the source. It is a sphere where you can put a heavy moderated source with putting the calibration source in it, but this is the source. And you see that there is nothing around because it's just wire that can move top or down the source. This is where they put the instruments. This is a phantom with 2 dosimeters in this picture. And interesting also that when it's not used, they put down the source in a hole filled with water. In such a case, they block everything coming from the neutron were not the source when not used. So that's something very, very interesting. What should be the interesting features for your facility? So if you can, it's not mandatory, but if you can, an automated source positioning system is helpful. You can also use a geometry like in this picture with four possibilities of irradiation if you have to make a lot of irradiation at the same time, because this direction, this one, you will have at the same distance exactly the same field characteristics. An automated calibration bench, which allows to move the distance from your detector without moving by yourself by hand, about from 50 centimeters to 3 meters. That would be my recommendation. And to have not one, but 2 americium barium source at the same place, because if you need to cover with such distances a wide range of dose equivalent, you need, for example, with a 510 to the 7, at 7.5 centimeter, you will have 1 millisievert, and at 3 meters, 60 microsievert. And if you want to go down at lower, you need another one from 10 to the 67 second minus 1 for the emission rate to cover down to 1 microsievert per hour. So why is this numbers? Is because it is in the different kind of standards you can find from ESC, from ISO. You have to verify the response of the dosimeters on a range that goes from 1 microsievert per hour to more than 1 millisievert per hour, and 1-2 points per decade. So you have not the choice. So this irradiator can be homemade or commercial. So I will not give you advices because I don't have experience of commercial system, but there are several on the market like Hopwell N40, Raker, etc. My recommendation is your first criterion is to see if there are as little matter as possible around the source itself. And if you want to have advice from experts, you can contact NMIs which have neutron calibration capabilities to get, okay, I have this model, what do you recommend for my need? Okay, so this is a calibration. So in theory, we just have a small source, a small detector, a parallel beam, and we can just apply this. It's easy, but in reality, you have such a kind of source surrounded with metals, a support, and you have a detector which is absolutely not a point, And the first question of the detector is, where is the calibration point within this volume? I don't know. Which is this the center? Is it front face? What is the distance from the source to the detector? It can be even more difficult if you consider dosimeters and several dosimeters put as a front face of a calibration phantom. What is the distance from the source to the dosimeter? The source is not a point, so you can have a variation of angles, also because the detector is not a point. But you also have background, neutrons coming from space, from ground. Is also, neutrons are not alone, as we have said, so could be photons mainly coming from space, coming from directly from the interaction of the neutrons within the source elements. And you have the air between the source and the detector. So the air has two effects. If you have a neutron will go in the wrong direction, it can be scattered back to your detector. Or if you go to the right direction, it's scattered out of your detector. You have support, and support means that all these elements will generate scattering neutrons. So scattering neutron first directly in the structure of the source, scattering and go back, scattering in the source support, scattering in the detector support. On all this interaction will generate also photons that can also reach your detector. But neutrons is also ionizing radiation, so means that people are not happy if they go outside because the neutron do not go through walls easily. So you need big walls and you need a room to confine everything. So putting a room with concrete floor, concrete walls, concrete roof will add additional scattering neutrons. So between theory and real world, it's not the same. So that's why what you will have to do to correct your reading of your device will be to take into account the instrument effective center, the geometric effect, because the fluence is not homogeneous over the entire detection area, to take into account the correction for scattering neutrons, the non-neutron ionizing radiations will have to be removed, the background will have to be removed, and you will have to be sure that you correct for the instrument linearity as a function of the fluence or dose equivalence rate, which is also could be the dead time if you have the count rate available. And all these correction and methods are described in a set of standards, which is a 8529 ISO series. So I just go back there. So the standards to start with is the 29661, which is just definition and fundamental concepts, will give you the main concepts and parameters. Then you have a first series, the first of the series of 8529 is characteristics and method of production. So that mainly focus on the neutron sources that could be produced by radioactive sources, reactors, accelerators, and give you some recommendation on how to produce a reference field using this kind of neutron sources. The part 2 is give you procedure to be used in order to calibrate radiation protection devices, and it has a particular emphasis on the radionuclide sources. It's less informative for other type of neutron sources. And the part 3 is the same, but more focused on individual monitoring and dosimeters. As you can see on the dates, the part 1 and part 3, sorry, there is a 3 here. And part 3 are very recent, 2021 for part 1, 2023 for part 3, and part 2 is being revised and will be published in the coming years. So this is an updated standard, so it's not the old one. Okay, so let's start with the effective center. So the effective center is a point the detector that determines the reference calibration distance. If you have a spherical device, that's very easy. The effective center is coincide with the geometric center of the device. But if you have anything which is not spherical, then you are facing some difficulties. So I give you an extreme example, which is a long counter. A long counter is a helium-3 counter, cylindrical here, surrounded by different layers of polyethylene to moderate the neutrons. How it works is you have energies coming from the front face, and they are moderated up to reach very low energy. At this and very low energy, they are detected by the helium-3 counter. If you have low energies, they will be moderated quickly and mostly detected in the front part of this detector. But if they have high energies, it will take more time and they will go deeper in mean and will be detected mainly in the rear part of the detector. And you see what it happens when you look at what is the effective center, which is a distance from the front face to the calibration position for the detector. You have a variation of 5 centimeters, up to 5 centimeters of distance, or where is the reference calibration point in this kind of detector, depending on the energy of the neutrons. And about this part, what is the effective center for dosimeter placed on a phantom? And there is today in the ISO standard, it is stated that the reference point of the to be used is the reference point of the dosimeter. It's a practical solution because when you change the angle, of the phantom to determine the HP 10, 60 degrees, 75 degrees, it will not change the position of the dosimeter. Everything is around there. But you can also consider that the reference point should be the front face of the phantom, so behind the dosimeter, because it's where the position of the body of the people is, because this is phantom is representing the body of someone. And there is another consideration: it should be 1 centimeter inside, because it's where the definition of HP10 is done, is 1 centimeter inside. And there are still not a full agreement within the neutron community on what is the best thing. So the recommendation is just make your choice, but indicate what is the distance you have chosen in such a case. Between the two, this one is less relevant. So the effective sensor, if you don't know it, now how could you determine it? So you should make measurement at several distances and adding in addition simulations if the full geometry of the detector is known. And you will compare the variation of the corrected instrument reading with the 1 over square of the distance law. And you will make this measurement will be a constant divided by the distance that you measure to the front face of your detector, plus this effective center you are looking for. Of course, this is only valid if you have corrected effectively at each distance your measurements for all the other parameters, scattered, geometry factor, and things like that. So that's not easy to be done. So if this is not available, and if it's too difficult to be determined, then the only solution is to put your detector at a sufficiently large distance in order that even an uncertainty introduced by not knowing the effective center will be kept at a reasonable level. Okay, now going back to the geometry correction. Why do we need geometry correction? Is because we have to use sometimes very short distances. Because testing the neutron-sensitive radiation protection equipment needs, if we want to follow exactly what is in the standards, to test them in equivalent rates up to a few tenths of millisievert per hour for survey meters and up to 1 sievert per hour for personal dosimeters. And if you really want to do it, it means that even if you have a huge 10 to the 8 second minus 1 emission rate for American beryllium, you have to put your detector at 3 centimeters from the source. And in such a case, of course, the field is not longer uniform over the whole front face of the detector, and the reading will exceed those expected from the inverse square law. So the source itself cannot be considered as a point. So what could we do? If you have a spherical device, and if you have an isotropic neutron field, then the ISO standard can help you and give you a geometry correction factor that can be calculated using this formula. I will not enter in details. And this is an example of what it gives. For a Californium source, it is a black line. You have a 10 to the 10.4 centimeter radius spherical neutron sensitive device. And you see that if you go at distances lower than 50 centimeter, then it has an increase of the correction to be applied to the reading that can reach, if you are at 20 centimeter, for example, about 10%. If you have a moderated Californium, it's even higher because of the size of the source by itself. In other cases, so not spherical devices, not isotropic neutron field, the only solution, or the best solution, is the Monte Carlo modeling. So anyway, you will need an accurate distance measurement. You will need a perfect knowledge of what is the effective center that we have seen just before, and you will have to add for that an additional uncertainty. So this geometry correction can generally be neglected if you are beyond 1 meter from the source. You can see, for example, here. So, because at 1 meter, you are as close as possible to a broad and parallel beam. But if you increase the distance, you will reduce geometry correction, but you will increase the contribution from the scattered neutrons, and you will limit the range of fluence dose equivalent rate you can have for calibration. If we look at the geometry correction for the HP10, so the equivalent dose, the personal dose equivalent, so geometry correction will increase with the phantom angle. So this is, for example, this is the angle of rotation of the phantom, and this is the correction compared to the angle 60. So you see that if you are at 60 centimeter, you will have a variation from about 5% compared to 60 degrees, and even 10% if you are compared to 75 degrees. And if you are at larger distances, of course, it's reduced by much, this effect. Another point is that you have not an homogeneity of the value of the dose equivalent on the whole surface of the phantom. So this is done by calculation done by NPL. So this is a variation of the dose depending on the position compared to the center of the phantom. So you will see that it will decrease if you reach the edges compared to the center. And once more, it can reach, for the American beryllium here, can reach about several % of differences. So what to do is to place the sensitive part of your dosimeters no more than 75 centimeters from the phantom center. So you reach in this direction where you can manage a few % variation only. To calibrate in a neutron field as close as possible to a broad and parallel beam, calibration distances of at least 1 to 2 meters, but you will increase the contribution of scattered neutrons. So that's why for the calibration of personal dosimeters, a compromise has been set up and proposed in the ISO standard is that we put 75 centimeter distances. Okay, so neutron scattering correction. So the neutron scattering correction is there because we have to estimate the difference of what we will do compared to the theoretical world, which is an ideal laboratory without air, without any material other than the detector to be calibrated. So the only solution will have to disguise yourself as a guy here and go it in space. So, but anything now with a neutron source without any surrounding materials, you will have also to put something stable. So two main contributions. So you have two main contributions of scattering corrections is the in-scatter. The in-scatter is anything that should not having reached your detector, but due to scattering is coming back. And the outscatter is a reverse situation. Anything that should have reached your detector, but has been deviated from its path due to the air or to anything he encounter. Okay, so at short distances, the neutron scattering correction is small if you have light source surrounding materials compared to the geometry correction. So you don't have to bother most the neutron scattering if you have a few centimeters from the source, but much more to the geometry correction. But if you increase the distance, mainly due to the room scatter, it will be more important to consider the neutron scattering than geometry correction. At long distances, so over 1 meter distance, it's a neutron scattering which is of primary importance. And why is it interesting to use large distances? In order to approximate a broad parallel beam, no more need to correct for geometric effect, to obtain low rates with a limited number of radionuclide sources, but you will have a maximum distance that you can use. If you remember, we should not consider conditions where the contribution of the scattered neutrons will generate an increase of 40% of your total reading. So this is, for example, what has been performed by Roberto Bedoni, and he presented this at the SSDL in a few years ago. So if you consider this kind of room, which is a square room, and here you have a few meters, and you calculate the number, the percentage of the reading of your device, which is due to the scattered neutrons, and this is the distance from the center of the source, you see that you will reach 40% at a distance of 1.25 meter. So you are limited if you want to strictly follow the recommendation in this standard. So there are several methods to correct for neutron scattering. So there is a shadow cone technique, generalized fit method, semi-empirical method, and the reduced fitting method. For the three-letter methods, so all these methods, are comparable if all the required conditions for their use are fulfilled. And what are their required conditions? For the three-letter methods, you need to have an isotropic neutron field. There are strong limitations concerning the type and geometry of the instruments, and it assumes that the source is positioned exactly at the center of the radiation room. If you don't match these conditions, the only solution, the only method that you can use and that will give you a good agreement between any simulation you can provide and measurements will be the shadow cone technique. And I will take a little time because my personal preference is really that we use and generalize this shadow cone technique. So the shadow cone technique is easy to understand. You have a source, you have a detector, you have direct neutrons, or you have scattered neutrons. And between the source and the detector, there is, let's say, a cone. And the shadow cone will just shadow this cone. It's made of 20 centimeter length of iron, 30 centimeter of polyethylene, can be also contain some boron to increase the absorption capabilities of the polyethylene, and it will stop the direct neutrons, but continue to measure the scattered neutrons. And if you simply make a difference between the reading made without this shadow cone minus the reading made with this shadow cone, then you have suppressed all the contribution due to the scattered neutrons. Of course, you have to correct because there is still this column of air between the two, and you have to correct for the air attenuation. So the shadow cone method is the only method which can be used for any type of direct reading neutron sensitive device. Whatever the geometry is, that works. It can also be used for electronic dosimeters placed on the phantom. Then you just hide the whole phantom, and the whole phantom is considered as the instrument. So could be considered as a reference experimental method, but it imposes calibration distances greater than about 1 meter, because you need 2 times the length of the shadow cone between the source and the detector. And it requires a set of 5 to 8 shadow cones in order to match all the source detector geometries, because what is required is that the shadowed surface, so the surface shadowed by your shadow cone, this is S2, should not be more than 2 times as large as the surface of the front face surface of your detector. So the shadow cone method also depends critically on the design of the shadow cones and its position. If you put it correctly, then you will measure a number of scattered neutrons here, which correspond to, which correspond to different kind of scattered neutrons in every directions. But if you place your shadow cone too close to the source, what happens? This kind of scattered neutrons, no problem, but you will cut part of those which could have impacted your detector after. So you will reduce the number of scattered neutrons you are detected. And the other place, if you put your shadow cone too close to the detector, important to say that all these 3 are covering the same, in the same way, the cone between the source and the detector. Just the size is adapted depending on the source. And this one is very close to the detector, and this one will reach, but the 2 others will be stopped. And you see a decrease. So there is a range where you can put it correctly, but you don't have to put it too close from the source or too close from the detector. It do not remove, shadow cone method do not remove the scattered neutron with direction within solid angle subtended by the shadow cone. For example, if I have a neutron which scatter within the source and then reach the detector, I will stop it as if it was a direct neutron, but it's not the case. So you have to remove this part, and the only way is to calculate it using Monte Carlo codes. It do not remove the air out scattered neutrons, and as we have said, it's limited to direct reading devices. What to do with passive detectors? You cannot use that. The only way, if you want to use this method for passive detectors, is you have 2 sets of comparables passive detectors, and you make measurements with the shadow cone and without the shadow cones, and from statistical analysis, you can remove the contribution from one to the others. If you use well this method, you can consider that you can add only an uncertainty of 3% on the scattering correction. So for example, if you have 40% of increase in the reading, it will only generate a 1.2% uncertainty on your final reading in the instrument. Okay, what's about now the neutron scattering and the personal dose equivalent? So we are in the case of passive detectors placed on the front face of calibration phantom. What could we do? So here it is a ratio between the value of the HP10 if you do not correct for direction, energy, intensity of all the scattered neutrons. If you do consider that you have a pure isotropic and direct neutrons only, you see that you will have at 50 centimeters, 10% variation, 75 centimeters, which is recommended, 15% of variation. If you include the energy distribution of your scattered neutrons, but you still consider that they're all coming in the same direction, so 0-degree directions, then you already decrease by a factor 3 the impact of these scattered neutrons. And if you include all the directions and energy intensities of all your scattered neutrons, then you will be at 1. So this is a nice study done by the CRIS, and that it's very nice to see that it is important to consider the scattered neutrons even if you are close to the source. Okay, in other cases, the calculated energy and direction distribution of the neutron friends with their uncollided and scattered components has to be made. So calculations always important there, and the contribution of the scattered neutrons to the personal dose equivalent, both in energy and direction, have to be taken into account. Okay, last point, which is important, is the linearity. Because at high dose or high frequency rate, your instrument is not linear. This is something which has been made by NPL and Neil Roberts. So he has shown that if you consider at low count rate this kind of instrument there, you start and you have something which is linear, and you consider it's linear, you will have this ideal response of the detector. But you see that if you increase the rates, and this is measuring in terms of dose equivalent rate, you see that it's not linear at all. And if you make just a measurement there and you consider, okay, I can make then an linear extrapolation, you will make something wrong. So that's why it's important to be tested. And the method is to measure at several rates, 2 to 3 points per decade. To have high rates, you have no choice than to be at very small distances. And the best way is you have 2 sources, instrument at the same place, 2 sources, one with high rate, one with low rate, and you test the 2. You already have an indication with 2 sources. And if you have only 1 source, then you have to make measurement at several distances. But of course, then you have to correct for scattered neutrons, use eventually techniques like shadow cone, but then you cannot go at small distances. So that's not very, very easy to be done. About the photon contribution correction. So there are, as I said previously, a lot of photons produced with the American barium. If you look at the ratio between the dose equivalent due to the photons to the dose equivalent due to neutrons is about 22%. So that's why generally there is a 1 to 2 millimeter thick lead cover that is placed around the source. It will reduce by about 1% the neutrons, but will reduce the ratio to a more reasonable level, which is 3.5%. And it can be explained here. So this is the rays of photon produced in an American barium. And you see that there are 4.4 MeV and then a lot of photons of lower energies. And if you put a cap of lead, then it will not affect this 4.4, but all the others will be reduced by much. And this is explained why this ratio is reduced such a way. So what to do in the ISO 8529 is to test the instrument with a cesium or a cobalt source of relevant activity to check if the photon contribution is negligible or not for your neutron detector. If it's negligible, then you have no more to consider it. If not, okay, then it's become more problematic, and you have to see how to remove the reading of the instrument due to the photons to reach the one due to the neutrons. So that's why I would recommend to use a cobalt 60 source, because mostly what you are interested in is a reading for this ray here. And the activity of the source to be chosen is in order that the dose equivalent ratio should be about 3.5%. It means you should have a cesium source which is 4 times the emission rate of the americium barium source, or if you have a cobalt, 2 times. But the best solution is by far to ask as the photon sensitivity of the neutron instrument has been determined before by your customer, because you are just there to produce neutron calibration. So you should ask it as a priori information that is required. Okay, I've talked a lot about Monte Carlo simulations. There are several codes that are available. You have MCNP, you have Fluka, FITS, Tripoli, Geon4 now, they have a new set of a new tool, which is Toucans. You have Serpent, certainly others that I don't know. I will not recommend. You just have to make your own experience and choose the one which suits you the best. My message is just this one. With such codes, it's easy to get a result, but it's hard to have a good one. So that's why you should always validate any calculation, any model that you do by measurements, and if possible with neutron spectrometry at several places. If you validate if you model all your facility, and then you make some neutron spectrometry, and that you match perfectly, which is hard to achieve, but match perfectly, then you have something by simulation, which is very powerful. But so this spectrometry should be done by some specialized teams, could come from NMIs or linked institutes. You have to estimate the uncertainties of the calculation, including deviation to the measurements, because the uncertainties given in your calculations, generally only statistical, is only a small and negligible part. And the simulation, which is experimentally validated, which has a good uncertainty evaluation, is I put but it is the only, in my knowledge, possible way to overcome difficulties if you are not in suitable irradiation conditions. You have a too small room, you have a lot of equipment surrounding the sources, you have no shadow cones, you have many dosimeter placed on a phantom, you have an unknown photon contribution, etc. So that's something to be considered. So conclusion, what you need to get started, you need a large room with, and I say large, is several, more than 12 by 12 per 6, no concrete walls if possible, but of course then you will face the radiation protection issues outside. At the center, and at least at 2 meters above the floor, an irradiator with, if you can, 2 americium barium neutron sources, about emission rates of 5, 10 to the 7, and 10 to the 6. In addition, if possible, corresponding cobalt-60 sources, about 100 megabecquerel for the first one and 2 megabecquerel for the second one, a set of shadow cones, an automated bench with support for instruments, shadow cone, and with a length greater than 3 meters, and advanced Monte Carlo simulation capabilities. Okay, but if this is a lot of effort, but with that, you can also be able to calibrate, provide calibration coefficient for neutron dosimeters, and then cover the needs of mostly all the workers exposed to fast neutrons. You can also provide a calibration coefficient for neutron survey meter. So I just show you here the response function in black curve is a response function. It's not a response function, it's a conversion coefficient to go from the fluence to the dose equivalent given by the ICRP 74. And this is the response function of 2 kinds of survey meters, so the Harwell and the Berthold. So they are not good. They are not good in this epithermal and low energy. But in the fast energy range, where we are looking for now, and above 20 MeV also there is a problem, but in the fast energy range, where we are willing to work with for most of the radiation protection problematics, if you calibrate it correctly at one point, it will cover mainly everything correctly for the response function, for the determination of the dose equivalent. And it will be good for nuclear power plants, for synchrotrons, particle accelerator, secondary neutrons at LINAC facilities, fusion facilities, particle physics laboratories, decommissioning activities, painful processing and transport facilities. And you can also provide calibration coefficient for neutron monitors. For example, there are neutron detections for leakage calibration of industrial equipment. You have homeland security, neutron analysis, performance of neutron generators, and you have even application in cement, mineral, and coal industries. So by just one sources, you are able in your country or to provide a lot of services to any users of neutron facilities. Okay, so now you have done this, you are happy, you are controlling everything. Could we do better? And what will be the next step? Okay, if you have an americium beryllium, you can complete, of course, first with a californium source and a heavy water moderated. It is complementary and can provide a wide reference spectrum. If you have a big market of calibration of neutron sources in your country, then maybe you can complete your facility with a manganese bath. If not, my advice is just send your sources to NMI, which has such facilities. And you can complete what you have with a small accelerator. So you have small neutron generators could be very compact. And if you have a DD1, you can provide 3 MeV magnetic field, which is an alternative to the californium. And if you put a tritium, so DT tritium generator, you can provide 14 MeV fields, but you will have to deal with the problem of tritium. And the problem of such small neutron generator is the stability, the monitoring, the lifetime. So my recommendation as a metrologist would be to have a dedicated real accelerator from 200 to 400 kilovolt air insulated, but that's not exactly the same budget to have such facility compared to a small neutron generator. You can complete with a thermal field. So if you have a nuclear reactor available, that's the best solution, but it's hardly something that you can find on the corner of your table. And if you have neutron sources, then you can also build, as it is an example here in Japan, it is a big block of graphite with several sources inside, and this gives you some thermal neutron field outside. And if you are a big institute, you can also complete with big facilities. So there are monogenetic neutron fields that can be produced with megavolt accelerators. There are only a few in the world. And higher than 20 MeV, we are still in our neutron metrology field looking to a reference facility, and that's why we are forcing to organize at EAA in July 2025 a workshop dedicated on this issue. So that's my last slide. So I would like to thank you for your attention. Just like to remind that the neutron metrology is a small community and it's a very collaborative people. So if you have any question, you can contact any member from CCRI Section 3, starting with the chairs, Andreas, Zimbal, and Roberts. You can also contact me as Executive Secretary, or you can also contact any people which is member of the CCRI 3 in all these countries where they are participating. And that's the end of my talk. Many thanks.